Hello class, this is Mrs. Ayodeji with today's video on sections 1.2 and 1.3, rate of change and linear functions. As you're watching the video, write down important vocabulary, formulas, equations. Feel free to pause, rewind, or replay the video as often as you need to get a clear understanding of what is occurring. And at the conclusion of watching the video, write a brief summary about what occurred in the video, and submit that summary as well as a top question via the online WISC. All right, let's begin. So we are going to be talking about section 1.2, which is about rate of change. And this may be a new phrase to you, but really it's something you've already been doing before in math class. And if you think about it, rate is how quickly something changes. And so when we're talking about a rate of change, we're talking about how quickly something changes, essentially. So this phrase, the average rate of change, is going to be very important, not only in pre-calculus, but also in calculus. And so the average rate of change or the rate of change, so sometimes they drop the average, but it basically means the same thing, of a quantity with respect to t over an interval can be found by the ratio change in q divided by change in t, or delta q divided by delta t. Now some of you may be familiar with the rate of change formula not using q and t, but using y and x. And some of you may say, oh, that's the same thing as slope. And for a graph, the average rate of change is basically the rate of change between 2 points on the graph, which can also be described as a slope. But as you may know, that graphs that are not straight graphs, but curved graphs, have different slope values. So in this case, this graph right here, if I take the average rate of change between this point and this point, I'm going to get a positive number. But if I take the average rate of change between this point and this point, I'm going to get a negative number. So for curved graphs, the average rate of change changes. So the slope, in other words, the slope of the line that connects the 2 points will change if you connect 2 different points, as you can see here. So that's why we call this an average rate of change, because if the function is not a straight line, then it's not going to be necessarily the rate of change of the function. It's going to be the rate of change of the line connecting the 2 points. And that's a very important distinction. But the average rate of change can also give us some information on an interval about whether or not the function is increasing or decreasing. And when we talk about increasing functions, we talk about functions that are increasing if the values of the dependent variable, in this case f, is increasing on the interval, let's say from a to b. Okay, so in this case, using this example up here, if my interval of a and b, here's a and b, as the function values continue over a to b, the function values are increasing, so it's increasing on this interval. But then for this interval, let's call this another a different a, and a different b, the function values are decreasing, which means the function is decreasing on this interval. Okay? As you can see here that the function increases and decreases over different intervals of the function, and some of you may be saying, well, what's going on here and here? Is the function increasing or decreasing over the interval? And we'll get to that. Okay, so we call it strictly increasing if the function values are always getting bigger, and strictly decreasing if the function values are always getting smaller. But how can we connect that with the rate of change? If f is an increasing function on an interval, then the average rate of change of the function with respect to t is positive. So think about that. As we can see here, delta t from a to b is always going to be the difference between b and a. And that's always going to be positive as long as a is smaller than b. Okay? And so if that's the case, then to determine if the function is increasing, we have to basically see if the change in the independent variable values are also increasing. In other words, if their change is greater, f of b, sorry, my handwriting is horrible with this, is greater than 0. Okay? So if f is a decreasing function, then the average rate of change of the function with respect to t is also negative on the interval. Now in this case, they talk about the entire function. So the entire function over the entire over every interval is increasing if the rate of change is positive, and the entire function is a decreasing function if the average rate of change over the interval is negative. And so here we have examples, and more nicely drawn examples in figure 1.11 and 1.12 as well. So this function is called an increasing function because no matter which interval you take where the right endpoint is greater than the left endpoint, the function values are going to be bigger, or the rate of change is going to be positive. And the same here, except the rate of change is always going to be negative. Okay? A way to determine if a function is increasing from the graph is if the function rises when read from left to right. So this is rises. And the graph of a decreasing function falls from left to right. Okay, simple enough. So let's take a look at a question about this function. On which intervals is the function increasing and which intervals is the function decreasing? As you can see, it curves, so I can tell you right off the bat which intervals the function is increasing and decreasing. So for increasing, I'm going to use green. From -3 to -2, the function is increasing because it's rising from left to right. From 0 to 1, the function is increasing because the function values are rising from f of 0 to f of 1. And from, let's say, around 2.5 to 3, the function is increasing because the function values are rising. For decreasing, the function values are decreasing from -2 to 0 because the function is falling from f of -2 to f of 0, and the function is decreasing from 1 to around 2.5 because the function values are falling from f of 0 to f of 2.5. Okay? Simple enough. So what's the function notation for the average rate of change? As we saw here earlier, it was the average rate of change is change in Q and change in T, or delta Q and delta T. And in this case, since Q is equal to f of T and the interval is from A to B, then the change of Q can be represented by f of B minus f of A, and the change in T can be represented from A to B, which is B minus A. Okay? So both of these mean the exact same thing, and this will be a very important expression when you get into calculus as well. All right? So let's take a look at this example. And as some of you may be saying, we're talking about the slope of a line that passes through the points f of A and f of B. And you're absolutely right. The average rate of change of a function over an interval is the slope of the line that passes through the points f of A and f of B. Okay? So, but we call it the average rate of change because this function does not have a straight line. Okay? Example 4, calculate the average rate of change of the function between x equals 1 and x equals 3. So that's going to be literally my A and my B. So my A is going to be 1 and my B is going to be 3. And then they say do the same thing when x is -2. So this is going to be my A, and x is 1. That's going to be my B. Okay? And as you can see here, this is not a straight line function. This is a curve function. So the average rate of change between x equals 1 and 3, and this is up here, It can be computed using this formula, and that's going to give me an answer of 4. And then the average rate of change for this, A and B, can be computed using this formula, and that answer, when we calculate it, is going to be -1. So as you can see here, for this function, the average rate of change changes depending on the interval that we're considering it over. Okay? So back to this original question, what is the average rate of change between this point and this point? Well, it's going to be defined as the slope of the line that passes through this point and this point, which looks to be a slope of 0. Let's go on to 1.3, linear functions. This should be a review. One thing about linear functions is they have a constant rate of change. In other words, the 2 points that you connect on any linear function is going to be the rate of change is going to be the exact same no matter which 2 points you pick. But let's take a look at an example of a mathematical model of the population of a town. The town population is 30,000 people, and it grows by 2,000 people every year. So the population is growing at a constant, that's a hint, constant rate of 2,000 people per year. So the rate of change is constant, and it's going to give you a linear function. And if this is the rate of change is 2,000, then when they ask you what's the average rate of change of P over every time interval, no matter what time interval you pick, from 0 years to 10 years, from 12 years to 13 years, from 19 years to 2,000 years, since the rate of change is constant, then you're going to have a constant rate of change, which is going to be 2,000. Okay? And since it starts at year 0 of 30,000 initially, then the y-intercept is 30,000. So you have different ways to express this linear relationship using a table, using a graph, and using a formula as well. So we should know this. A linear function has a constant rate of change, and the graph of any linear function is a straight line. And because I have a function that represents this population, I can predict the population 1,000 years from now by plugging 1,000 in for t and getting the answer, or continuing this graph until it's 1,000 years and looking to see where the function value is. Other financial, there's other models, in this case a financial model, that can be represented by a linear function. A small business spends $20,000 on new computer equipment and for tax purposes chooses to depreciate it to $0. Depreciate it means to decrease in value. Okay? So the depreciation is going to end up being $0 at a constant rate over a 5-year period. So in 5 years, the value of the business is going to be $0. So the question is, what's the rate of change? Well, average rate of change or rate of change? Well, if it's going to be a change of $20,000 in 5 years, the average rate of change is $4,000 per year, negative $4,000 per year. So I can tell you, based off this rate of change, what the table of values is going to be from year to year. I just decreased $4,000. I just decreased $4,000. Okay? And then I can come up with an expression that represents it. This represents the slope, or average rate of change, and this is the starting point, which is 20,000. Okay? Every linear function can be represented by something that looks like slope, or growth rate, or depreciation rate, depending on the type of situation we have. Here the growth rate was negative, so it was actually a decreasing rate. Number of years, which would be representative of a variable, usually x, but in this case we're dealing with models and it's going to be time for t, and then an initial population or initial value. In this case it was $20,000 for the value of the car, and in this case it was initial population of 30,000 people. Okay? And there you have it. And this should look familiar about what you've learned.